Assalamu alaikum everyone. Today we are going to start chapter number 2, lecture number 7, and this chapter will be about custom single purpose processor design. Previously in chapter number 1 we have talked about embedded system. There was an overview of embedded system. Then we talked about the different technology, the processor technology, the IC technology, the design technology, design challenges, and we have computed some design metrics, and finally we finished our last lecture on design methodology. In today's chapter we are going to discuss the custom single purpose processor with the help of few examples, and at the end of this chapter we are going to optimize the custom single purpose processor. So let's start chapter number 2, lecture number 7. So in introduction, processor is digital circuit that perform combinational tasks. As you can see in this example, we have an example of digital camera which comprises of many coprocessor, which comprises of general purpose processor, which comprises of controllers, LCD units and display units, multipliers, multiplexers, lens. So a processor has a controller and data path. There are two major components of a processor, that is controller and data path. General purpose processor performs variety of computational tasks. So this is our general purpose processor here, which can perform variety of tasks. Single purpose processor perform only one particular computation, whereas custom single purpose processor perform non-standard tasks. For example, JPEG. This is a processor that is going to perform non-specific, non-standard tasks. A custom single-purpose processor may be fast, small, low power, but it has high NRE cost, obviously because we are going to design something that is custom. So the non-engineering recurring cost will be very high and longer time to market because we have to design something from scratch. However, this won't be more flexible. This will not be more flexible because this is non-standard and it is going to perform only one particular task. A general purpose processor designed such that it can carry out a wide variety of computational tasks, which are described by a set of programmer provided instruction. In contrast, a single purpose processor is designed specifically to carry out particular computation. While some tasks are so common, we can purchase standard single purpose processor. For example, this is our standard single purpose processor. This is our standard single purpose processor. So these are common tasks, and for these tasks we can purchase standard single purpose processor to implement those tasks. Others are unique to particular embedded system. Such custom tasks can be best implemented using custom single-purpose processor. An embedded system designer may obtain several benefits by choosing to use a custom single-purpose processor rather than general-purpose processor to implement a computation task. First, performance may be faster due to slower clock cycle. As I have already told you that custom single processor are going to be faster due to fewer clock cycles resulting from customized data path, and due to shorter clock cycle resulting from simpler functional unit, fewer multiplexer or simpler controller logic. So everything is going to be very reduced in size, whether it's functional unit, whether it's control logic, whether it's data path, multiplexer. Second, size may be smaller because it is going to perform a very particular operation. However, that particular operation is non-standard, means that it is not so widely used. Okay, and one more important thing, that it does not have any program memory. Once it is programmed, its program cannot be changed. Okay, lastly, power consumption may be less due to more efficient computation. However, cost could be higher, as I have already told you, because of high NRE costs. Since we may not be able to afford to invest as much as NRE cost as can designer of mass-produced general purpose processor, performance and size could be worse. So obviously we cannot spend as much as of NRE cost as a general purpose processor designer can spend. So the performance and size could be worse. Time to market may be longer, flexibility reduced compared to general purpose processor. So we have like drawbacks of time to market, flexibility, NRE cost, and size and power. However, if we produce large amount of volumes, the size and power can be fast as shown in slide. Techniques for designing customer purpose processor. We start with a review of combinational logic and sequential design, and we describe methods for converting programs to single purpose processor, that are custom single purpose processor. So moving on to next slide. So one of the most important building block of combinational logic design and sequential logic design is CMOS. CMOS transistor on silicon, that is complementary metal oxide transistor on silicon. This transistor is used to make logic gates. A transistor is the basic electrical component in the digital system. Combinational of transistor form more abstract components called logic gates. So by combining transistor we form a more abstract components called logic gates, which designers use when building digital system. Thus we begin with short description of transistor before discussing logic design. A transistor acts as a simple on-off switch. One type of transistor, complementary metal oxide, is shown below. As you can see, it has a source, it has a drain, it has a gate, and it is made up on silicon substrate. One thing should be clear, that the gate here is not a logic gate. Okay, this gate is not a logic gate. We have two types of CMOS available. Number one is NMOS transistor, number two is PMOS transistors. So this CMOS conducts, that is NMOS conducts if the gate is 1, that the gate logic is high. Okay, so voltage at the gate controls whether current flows from source to drain or not. Please do not confuse the gate with logic gate. Okay, moving on to next slide. So in this slide you can see lots of CMOS transistors. We refer to logic levels typically 0 when 0 volt is applied and 1 when 5 volts is applied. There are two types of CMOS. NMOS conducts when gate level is high and PMOS conducts when gate level is low. Hence these are called complementary. Basic gates that we are going to use are inverter, NAND or NOR. So in NMOS, if gate is 1, this transistor conducts. In PMOS, when gate is 0, this transistor conducts. We can make inverter by using both NMOS and PMOS. So in this, if we apply X is equal to input is 0, the upper transistor conducts and 1 will output. Okay, so if we apply 1, the lower transistor conducts and 0 will appear. So inverter. Whereas in this NAND gate, if any of the input is 0, if either X is 0 or Y is 0, the upper transistor turns on and 1 will appear here. Okay, so either this is 0 or this is 0, 1 will appear here. If both are 1, none of the transistor will conduct and 0 will appear here. Whereas in the case of NOR gate, okay, if we have both zeros, if X is 0, Y is 0, this will conduct and we will have 1. In rest of all these conditions, if any of X or Y is 1, if either X is 1 or Y is 1, the output will be 0. Okay, because this will start conducting and everything goes down to ground. Clear? Okay. So that was the basic function of all these inverter, NAND gate and NOR gate. And these are the basic gates that we are going to use. That was about it. Let's move to next slide. Digital system designers usually work at abstraction level of logic gates rather than transistors. So we work on logic gates, okay? Rather than transistor, we work on logic gates. This figure describes 8 basic logic gates. Each gate is presented symbolically with Boolean equation. So this is the Boolean equation. This Boolean equation. Okay. And with the truth table. So this is truth table, where we have inputs. This X is input and this F is output. This X and Y are input and this F are output. Similarly, F is output and this is input. So inputs are on left side and output is on right side. The AND gates output 1 if and only if both inputs are 1. So we can check here the AND gate. The AND gate is 1 when both the inputs are 1. The OR gate outputs 1 if any of the input is 1. So here in OR gate we can check it outputs 1 if any of the input is 1. The XOR gate outputs 1 if and only if exactly one input is 1. So XOR, we can see this, it outputs 1 if one of the input is 1. The NAND, NOR and XOR gates output the complement of OR, AND, OR or XOR. So complement, complement, complement. So you can see here 0, 1, 1 transform to 0, again 1 transform to 0 and then finally 1, 0. So XOR complement is XNOR, OR complement is NOR and AND complement is NAND. Now the important thing is that even though AND and OR gates are easier to comprehend logically, listen carefully. Even though AND and OR gates are easier to comprehend, it means easier to understand logically, NAND and NOR gates are more commonly used. We can see in the previous slide that I haven't explained you AND or OR gate, rather we use NAND, NOR and inverter. Those are the gates we built using transistor. The NAND could easily change to AND. You can see that if we put an inverter in front of NAND, it can be changed to NAND. Or the NAND could easily change to AND by changing the top one on the to 0 and 0 at the bottom. So let's move to previous slide. So if you go to previous slide, if we change 1 to 0 and ground 0 to 1, we can transform NAND to AND. Is that clear? I hope that it is clear. The NOR could be changed to OR similarly. Like in the top one, we can replace it with 0 and the bottom ground will be replaced with 1. We can have opposite functionality. But it turns out that PMOS transistors do not conduct 0 very well. Now listen carefully. But it turns out PMOS transistors do not conduct zeros very well, though they do find conducting ones. So PMOS transistors do not conduct zeros very well. They do fine conducting wells. Likewise, NMOS transistors do not conduct 1 very well. They do fine conducting zeros. Hence, NAND or NOR gates prevail over AND or OR gates. Okay, let me repeat for you. The PMOS transistor do not conduct well for 0, whereas NMOS transistor do not conduct for 1. So that's why like there is some sort of leakage or there is some sort of like issue. So we do not use AND and OR, rather we use NAND and NOR. So in this slide, a combinational logic circuit is a digital circuit whose output is purely a function of its present input. Such a circuit has no memory, past input. We can use a simple technique to design a combinational circuit from our basic logic gates. We start with the problem description. So the problem description is that this is our problem description. Y is 1. So here Y is 1. If A is 1, so A is 1, Y is 1. Okay. Then we have or B and C are 1. So here B is 1. So again 1. So now this A is 1. So this is 1. So A is 1. This is 1. And B and C are 1. B and C are 1, so Y is 1. Okay, so here this was not correct. Okay, now what about Z? Z is 1 if B or C is to 1. So B or C, B is 1 here, so Z is 1. B is 1 here, C is 1 here, so Z is 1. So 2 Z's and like 1, 2, 3, 4, 5 Y's. So now we have a truth table. We can translate this description to a truth table with all possible combination of inputs on the left and desired outputs for each combination on right. This is what we have done so far. Now we can then translate this into equation. So we have translated this to equation. So description, truth table, now this to our output equation. So for Y, A bar, so let's remove this. So I'm just going to tell about A bar. So this is for Y, so A bar, okay, B and C, this. After that A, B bar and C bar, A, B bar and, oh that's some issue. Let's remove this. Okay, remove this. So A bar, B, C, A, B bar and C. So this is how you can write your output equation for Y, and for Z let's look at this A, B and C. Okay, so now the thing, next point is to minimize output equation. So how we can minimize output equation? We can use K mapping. So we have 3 inputs and 1 output. This is how we can use 0, 0, 0. So 0, 0, 0, 1. This is 1, 0, 1, 1. This is 3, and then we have 0, 1, 0. So 0, 1, 2, 3. 0, 1, 2, 3. Okay, so why we have 0, 1, 3, 2, not 2, 3? Because we can have only 1 bit change. Okay, because we can have only one bit change. So for example, now this one is 0 1 1. It means A bar B C. Okay, this one A bar B C. Now writing all these, we can find out the common points. Here we have only A common, okay, because this is A, and then we have, what is common here? We have BC. So now the equation is reduced to A plus BC. And now coming to Z, we have A bar B bar C, A bar BC, A B bar C plus A B C bar and ABC. So just writing them in their appropriate boxes. For example, ABC is 1 1 1. Okay, so this 1 1 1. Okay, this one. Now writing rest of these. So what is common here? We have common. What is common here? We have B bar C. This is. What is common here? We have B C bar. And what is common here? We have A, because this is A, and common is B. So AB. Now once you have Y and Z, we can make this logic circuit, and everybody knows that how we can make this logic circuit. For example, for Y is equal to A plus BC. This is your Y. So it means we need to use OR gate. This is OR gate, and this A is going straight here, B and C and this is B and C and then this is OR, and rest of this is for Z. You can do it yourself. Okay, I hope this is clear. So in this figure you can see like 1 2 3 4 5 basic combinational logic components. Although we can design all combinational circuits in this manner, large circuit would be very complex to design. For example, a circuit with 16 inputs would have 2 raised to the power 16 or 64k rows in its truth table. One way to reduce the complexity is to use combinational components that are more powerful than logic gates. So these are our combinational logic components, 1, 2, 3 and 4, 5. So we cannot have large number of truth table. For example, if we have 16 inputs, we can have 64k rows. So one way to reduce the complexity is to use combinational components then that are more powerful than logic gates, which we have seen previously. So combinational component often called register transfer or RT level components. So these are RT level components. Okay. So now here number 1. A multiplexer, sometimes called a selector. Why we call selector? Because we select the data inputs, allow only one of its data input. Here we can see that I0, I1, up to IM-1 RT data inputs to pass through output. So this is output, this is output O. Thus a multiplexer acts much like a railroad switch, allowing only one of the multiple input tracks to connect to a single output track. If there are m data paths, important thing, then there are log to the base 2m select lines. Okay, we call this an m by m multiplexer, meaning m data inputs and one data outputs. So here these are data inputs and this is data output. Okay, and these are your select lines. So for if we have like 8 data inputs, we need to have 3 select lines. If we have 16 data inputs, we need to have 4 select lines. Okay, the binary value of S determines which data input pass through. For example, if we have 0 0 0 means I naught passes through. If we have 0 1, it means I1 passes through. If we have 1 0, it means I2 passes through. For example, an 8 cross 1 multiplexer has 8 data inputs and thus has 3 select lines. If those 3 select lines have value, if we have value on the select line 1 1 0, okay, so it means 1 2 4. It means I6 will be on the output. So if I6 is 1, O will be 1. If I6 is 0, output will be 0. Okay. Now moving on to decoder. This is decoder. Okay. This first one was multiplexer. The second is decoder. Another combinational component is decoder. A decoder converts its binary input I into a one hot output. One hot means that exactly one of the output lines can be 1 at a given time. Thus, if there are n in outputs, so we can see these are output n outputs and these are n inputs. Only one output can be active, rest of these will be 0. Thus, if there are n outputs, there must be log to the base 10 n inputs. Okay. We can call this log to the base 2n into n decoder. Clear? Log to the base 2 into n decoder. For example, now listen carefully. A decoder of 3 into 8. Okay, 3 cross 8. Decoder has 3 inputs and 8 outputs. So if input is 0 0 0, then the output will be O naught. Okay. If input is 0 0 1, output will be O 1. Clear? A common feature of a decoder is an extra input called enable. There is an enable bit. It is not shown here, but a common feature of decoder is an extra input called enable. When enable is 0, all outputs are 0. When enable is 1, the decoder function as it was working before. Now moving on to our adder. So an adder adds two n bits binary data inputs A and B, generating an n bit output sum with an output carry. For example, a 4-bit adder would have 4-bit A input, a 4-bit B input, a 4-bit sum output and a 1-bit carry. If A is 1 0 1 0, if A is 1 0 1 0 and B is 1 0 0 1, so in that case sum would be 0 0 1 1. Okay, and carry will be 1. Is that clear? An adder often comes with carry input also, so that such adders can be cascaded to create larger adders. So you can have 2-bit adder and you can use this 2-bit adder to cascade with another 2-bit adder. So that carry output will be another input for some other summer. Okay, now next is comparator. This is our comparator. A comparator compared two n-bit inputs A and B. These are inputs and n-bit inputs, generating outputs that indicate whether A is less than, equal to or greater than B. So if A is less than B, less pin will be 1. If A equal to B, equal pin will be 1. And if A is greater than B, greater pin will be 1. Okay. So now finally we have ALU. So ALU is just like your adder. It's just going to perform more operation as compared to adder. It's going to perform addition, summation, all that. An arithmetic logic unit can perform a variety of arithmetic and logic functions on its n bits A and B. Now, How we can perform? You can see there are select lines. It means that a mux is there. So if we have select line 0, 0, 0, or for example, like if it was performing 8 different operations, so we need to have 3 select lines. Okay. So for example, on 0, 0 it performs addition, on 0, 0, 1 it performs, let's say, subtraction, on 0, 1, 0 it performs AND operation, and some other select line it perform OR operation. Okay. So finally there is another common registered transfer level component which is not shown here, is a shifter. Now listen carefully. A n-bit input I can be shifted left or right and then output to an output. For example, 4-bit shifter with an input 1010 would output. So a shifter, if the input is 1010, the output will be 0101. So what happens? We have shifted towards right position. Okay, we have shifted towards right. So now this is gone and a 0 has come behind 1. Okay. So shifters usually come with an additional input indicating where you want to shift, right shift or left shift. Which bit needs to be shifted out. Here in our case 0 is shifted out. Okay, so it is known as right shift. Moving on to next slide. So when we talk about sequential logic, one thing that appears in mind is flip-flop. A flip-flop is a sequential circuit whose outputs are a function of present as well as previous input. So now the difference between sequential components and combinational components can be clarified, that in sequential components the output is a function of present as well as previous input, whereas in combinational logic the output is a function of only present inputs. In other words, sequential logic possesses memory. One of the most basic sequential circuit is a flip-flops. Okay, so all these, this one, this one, this one, all these, you can see there is a clock with arrow. Okay, so all these possesses flip-flop because they are going to depend upon their previous inputs. A flip-flop stores a single bit. The simplest type is the D flip-flop. Now listen carefully. It has two inputs, D and clock. When clock is 1, the value of D is stored in flip-flop. Okay, when clock is 1, the value of D is stored in flip-flop and the value appear at the output Q. When clock is 0, the value is D is ignored and the output Q continues to reflect stored values. Okay, so nothing new appears as long as the clock is 0, but when the clock is 1, the current values appeared at the output. Okay. Another type of flip-flop is SR flip-flop, which has three inputs, SR and clock. When clock is 0, the previously stored bit is maintained, okay, and appears at Q. When clock is 1, the input S and R are examined. Okay, when clock is 1, S and R will be examined, otherwise the output will be remain as it was before. If S is 1, a 1 is stored, okay. If S is 1, a 1 is stored. If R is 1, a 0 is stored. If both are 0, there is no change. It means there is no change. For S means set, set means 1. R means reset, reset means 0. If both are 1, behavior is undefined because we cannot have setting and resetting at the same times. Okay. So when we have setting and resetting at the same time, nothing will, this condition is not defined. Thus, and there is another common type of flip-flop which is known as JK flip-flop, which is the same as SR flip-flop except that when both J and K are 1, the stored bit toggles. Okay, when both are 1, as in previous case when S and R were 1, it was not defined. But when J and K are 1, the output will toggle. If it was 1, it will go to 0. If it was 0, it will go to 1. To prevent unexpected behavior from signal glitches, Flip-flops are typically designed to edge triggered, meaning they examine their non-clock inputs. Okay, so they are edge triggered, not level sensitive. When clocking is rising from 0 to 1 or alternatively, so they change their behavior when clock is either rising or when the clock is falling. Okay, so here in this slide you can check this out. A register store n bits. So this register store n bits data input I. You can see here this is data input I. With those stored bits appearing at its output. So these stored bits will appear here at Q. A register usually has at least two control inputs. You can see that these are two control inputs. Load and clock. This load and clock. For a rising edge trigger register, the input I are only stored when load is 1. So when clock is 1 and load is 1, the data will be loaded to the register. The clock input is usually drawn as a small triangle as shown in the figure. Another common register control input is clear. You can see this is clear. Okay, last one. Which resets all bits to 0 regardless of the value of I. It doesn't matter what is the input. If clear bit is high, it will clear everything. Because all n bits of the register can be stored in parallel, we often refer to this type of register as parallel load register. Okay, so this is parallel load register. All the bits are loaded in parallel. So this is different from shift register. Okay, make sure. So when load is 1 and clock is high, that is rising edge, I will be loaded and it will appear at the Q. When clear is 1, clock is high, everything will be cleared. Okay. Now a shift register stores this shift registers. This shift register stores n bits, but these bits cannot be stored in parallel. As I've told you that these bits are stored or appeared at the output in parallel. However, in this case, the bits are not stored in parallel. Instead, they must be shifted into registers serially. So the bits are shifted here serially. Okay, meaning 1 bit per clock edge. So 1 bit is shifted at per clock edge. A shift register has a data input I and least two control inputs. So there are two control inputs. Number 1 is shift, number 2 is clock, and this I is data. Okay, so what happens is that when a clock is rising, shift is 1, shift 1, clock is high. So what happens? The nth bit is stored in n-1. So nth bit is stored in n-1. So it means it 1 shifted. Another n-1 will be stored in n-2. So 1 is shifting. Okay, so this is shift register. Because this is cannot be stored in parallel, it is serial. Okay. Now finally about this final counter. A counter register that can also increment, meaning add binary 1 to its stored binary value. So it basically counts, and a counter is a register that can also increment, meaning add binary 1 to its stored binary value. In its simplest form, a counter has a clear input. So it has one clear input. It is not shown over here, but this is clear, and this one is count. Okay, the top one is count, the center one is your clock. So in its simplest form, a counter has a clear input which resets all stored bits to 0 and a count input which enables increment on each clock edge. So this counter increments on each rising clock. Okay, and the increment is determined by this count. A counter often also has a parallel load input and associated load control signal. A common counter feature is both it can count up and it can count down, requiring an additional control input. However, if we don't have any additional control, so this is only up counter, it will not count downward. These control inputs can be either synchronous or asynchronous. Asynchronous inputs value only has a effect during clock edge. A asynchronous input value affects a circuit independent. So these are all 1, 2, 3. These are all synchronous because these sequential components are working with respect to clock. Okay, so these are synchronous. Whereas these clear lines, this clear line, this clear, this clear, the clear line is asynchronous. It means when clear is 0, independent of the clock. I might have said wrongly, but independent of the clock, when clear is 0, everything will be clear out. So clear is asynchronous, whereas loading, shifting and counting is all synchronous. It means rising edge. Okay, let's move to next slide. Now, based on the sequential logic components that we have discussed in previous slides, let's have an example of sequential logic design. Now, the problem description is you want to construct a clock divider. So we want to divide a clock. Slow down your pre-existing clock so that you output a 1 for every 4 clock cycles. So the thing is that we need to determine 4 clock cycles. So once we get 4 clock cycle, we will like update the clock. So after 4 clock cycle, we assume that there is only 1 clock cycle. So we are like slowing down the clock cycle. So for this thing we need state diagram. Okay, we need state diagram. This is our state diagram. So this A is our input, this A is input, X is output. Okay, A is input, X is output, and this Q0, Q1 are input state, and this I0 and I1 are output states. Why we have Q0 and Q1 2 bits? Because you can see 1, 2, 3 and 4. So 0, 0, 0, 0, 0, 1, 1, 0 and 1, 1. These are our 4 states. So we start from 0, this point, just look at yellow marker. We start from here. We move to 1 only when A is equal to 1. We move next forward when A is equal to 1. So 2 clock cycle. We move again when A is 1, 3. And we move again when A is 4. So on 1, 2, 3. At this point X become 1s. Means after 0, 1, 2, 3. So these are like 4 clock cycles. So after 4 clock cycle, X is equal to 1. So we construct a truth table. 0, I'm going to use this green marker. So 0, 0, 1, input is 0, 0, state is 0, 0 and input is 0. So means we are here at 0. Output is 0, 0. It means we are not going anywhere else as long as A is 0. So X is 0. Now let's talk about this final one. When state is 1, 1, it means we are at 3. And A is 0. It means we are not going anywhere. So we are at same state. But output is 1. Okay. Again, when the input state is 1, 1, the output state is 0, 0. It means we are moving forward because A is 1. Okay. It means that clock cycle are exceeding. So after 4 clock cycles, either input is 0 or input is 1, output will be 1. Sorry, this down 1. This output will be 1. Either A is 0 or 1. Clear? So we have problem description, we have state diagram, we have state table, and obviously we need to have implementation model before, but I have explained you state model before. So we have combinational logic. Why we have combinational logic? Because of this. This is our combinational logic. Okay. So you can see in our combinational logic, this is our input, this is output, this is output states. Okay. And these are input states. So in combinational logic, we are getting input states and output states, input and output. And how do we get to next states? So for that we need state register. So given this implementation model, sequential logic design quickly reduces to combinational logic design. So this was sequential. Okay. So sequential model reduces to combinational logic. This is what you need to understand here. Okay. Let's move on to next slide. So once we have combinational logic in the truth table, we can find out I naught and X, and this is exactly the same, 3 inputs, 1 output. So we need to have like K map, P map, and now we have these Boolean equations, so we can convert. This is now your combinational logic. How we can obtain this combinational logic? We obtain this combinational logic using the what? Sequential logic. Okay, sequential to combinational logic. Okay, I hope this is quite clear now. So this is how a custom single purpose basic processor model looks like. uh, for now we have seen like how we can transform a sequential logic to combinational logic. So now we are going to look at the custom single purpose basic model. So if you look here, there are 2 important things. Number 1, controller. Number 2, data path. If you look further down, like in detail, we have this controller and we have this data path. Now we have control input, which we call external control inputs, external control outputs. We have external data inputs, we have external data outputs. So we have like 2 things: a controller inputs, controller output, data path, data inputs, and then there is a communication between data path and control. Okay, so if you go and look inside the data path, let me rub this out. Oops. So in data path we have registers. Obviously we have to store some values. Okay, obviously register requires clock, and then we have functional unit. Functional unit means your ALU, and in controller we need to have control logic and state register. Why we need state register? Because we need to get to next state, and these are your external data outputs, these are your external control output, these are your external control input, these are your external data output, and this is control signal coming in, data signal going out. So this is the basic architecture. Like we have data path and we have controller. In controller we have next state and control logic and state register. Moving on to next slide. So this last slide is about the example of greatest common divisor. So what we are going to do now, we're going to make a custom single purpose processor, and in this custom single purpose processor we can apply the combinational and sequential logic design technique described earlier to build a controller and data path. What we want to do, we want to make a controller and a data path. Therefore we now describe the technique to convert computational tasks into a custom single purpose processor consisting of controller and data path. We begin with a sequential program describing the computational task that we wish to implement. Okay, so as you can see in this figure, the figure that is shown here, this figure, let me point it out, this figure. So this is a task that we want to implement. This one shows a black box. We only knows like there are three input, go underscore I, x underscore I, y underscore I, and it computes the GCD, and this D underscore O is the data output. The system functionality is straightforward. To output should present the GCD of input. So for example, if we have 8 and 6, its GCD is going to be 2. So if this is 8, this is 6, this is 1, output should be 2. So this is the code which is given below. First create an algorithm. This is the algorithm. Okay. Convert algorithm to state machine, known as finite state machine with data path. So this is state machine. Okay. We haven't used, I will try to teach you about the template in next lecture. For now, just try to understand how the GCD is compute, and then we will look at the flow diagram. So we have like 9 steps, 0 to 9, total are 10. So how desired functionality is achieved? We first declare two variables x and y. While 1, as long as the condition is true, it means that we are inside a loop. While not, go underscore I, obviously it means like 1, as long as this condition is true. So whatever there is in x underscore I, this x underscore I will come into x, and whatever is x underscore y will come in y. While x is not equal to y, so 8 and 6 not equal. Okay, x is less than y, no, so it won't go into this. Else x minus y, so 8 minus 6 will be 2. Okay, so now x is equal to 2, y is equal to still 6. Okay, now again let me rub this. Now moving again, now x is less than y, yes, x is 2 and y is 6, so y minus x, so y minus x will be 4. Okay, y is equal to 4. Else it won't come in else because one condition is true. Next time, now y is 4 and x is 2. Now let me rub this and clear this out as well. Okay, so x is less than y, no, so it will come into this one, x minus y, no, sorry, x is less than y, yes, x is less than y, so y will become 2, and x is already 2. Okay, x is already 2. So again, while x is not equal to y, now y and x both are equal, so 2 is equal to x, so which is 2. So this is how you compute. This condition is only for getting the program ready, like to keep the things moving. Go underscore I, as long as this is going to run infinitely, okay, because of the semicolon. So as long as go underscore I is 0, not will be 1, so while 0, okay, so go underscore I will be 0. So if you look at the flow chart, you can see it yourself, like this is your while I, if not I, it will go and stop. Okay, this is it. Okay, otherwise if while is true, while 1 is true, it will go here. Now it will check again. If go underscore I is 0, if go underscore I is 0, it will come here. Okay, it will stuck here. Otherwise, if it's 1, it will come here and it will assign the value of x underscore I in this and this. So this is a jump between 2 and 2j. So that's why we have labeled 2 minus j. Clear? Now, after assigning the values, we can check that there is a while on x not equal to y. So this is a condition on line 5. X is not equal to y, it will come down. Okay. Otherwise, if x is equal to y, it will come here straight away. Sorry, this point. Okay, do is equal to y. Now, further I have explained to you, if x is less than y, there will be a change in y. If x is greater than y, there will be a change in x. And then we have 6 minus j, because we have a, why we have this jump statement? We need to match this with this, okay? And then we have this jump. If x is equal to y, it's going to come here, and then okay, so let me just recap for you. Let me rub it for you and then come from here. So this thing is keep on repeating as long as x is not equal to y, okay? And this will happen if x is equal to y. So just make sure 5 and 5j, okay? And then 6 and 6j, because we are comparing two things. So we need to have a jump that goes back, okay? So this is quite simple, just practice it out and things will be very clear to you. So in next lecture we are going to make a finite state machine, complete finite state machine, and we are going to use template, and finally we are going to like optimize this. So like you can see, currently we have like 0 to 9, like 10 steps, that 10 states we have to pass in order to compute the GCD, and this process is quite iterative, this process. So we will look into the optimization method, how we can reduce the states. Okay, and that's it for now. Take care, Allah Hafiz.